Today we are going to do section 2.7 on page 228. First, the cylindrical coordinates. What's that? That's the same as polar coordinates except with a z coordinate, a third one. So it's that's why it's called cylindrical. So the base is a circle, but we have a vertical. The z doesn't change though. So then as a result, then everything from polar coordinate applies. Look at the next page. We have a graph to show you where it goes. And now, if you're not sure what this means, stare at this graph and you will get it real quick. See, theta is the angle, xy plane is on the bottom, right? So then you have, what is that? That is, I can't see that thing. What is that? That is, we don't care. The point, I think that's r. Yeah, that's r. Never mind. Anyway, so r is the hypotenuse, and you have x and y, and there's theta is the bottom angle. So the point, which in rectangular coordinates is called xyz, in cylindrical coordinates is called r theta z. Okay, and in this definition, then the conversion is all in theorem 2.15, where x is r cosine theta, just like polar coordinates, y equal to r sine theta, z is just z. And then r squared is x squared plus y squared, again, just like polar coordinates. Tangent theta equals to y over x. And so then at this point, everything looks almost the same, except that theta, we restrict theta to go from 0 to 2 pi. That way it is unique most of the time. If the theta, if x is 0, being the tangent theta is y over x, if x is 0, then the value of theta is pi over 2 or 3 pi over 2 or even 0, depending on the situation. Now, having said that, let's look at the next page and then look at the different situations. I'm looking at page 230, where you have a bunch of surfaces. Now the top surfaces are what in the original xy coordinate, okay? In the xy coordinate, if x or y or z equals to some constant, you get a plane. But in the new one, if x, y, and z equals, which we have r, theta, and z, in this case, z equals the constant is still the same plane because z hasn't changed. But when r is a constant, the radius is a constant, so you get a cylinder. And when theta is a constant, you get what's called a half plane. That is, the plane goes from 0 and from 0 all the way out to making the angle theta with the x-axis. So that's that. And having said that, let's look at the next page where example 2.60, you convert from cylindrical to rectangular coordinates. Please do that as part of your homework next. And the next example, converting from rectangular back to cylindrical coordinates. Again, please do that as part of your homework. And then the next one, you have to identify surfaces. Then, do that too as part of your homework. That's also very straightforward. You just plug stuff in and see what it is. Or alternatively, can even, well, I haven't done this in the Desmos calculator yet. I don't know if it can do the cylindrical system. It's not that interesting. It just, please do example 2.62. It's also very straightforward. Next, let's look at page 235, spherical coordinates. The spherical coordinate system is where you have three things represented. There is rho, which is the distance, which stands for radius, by the way, the Greek letter rho. And then you have theta, which is the angle at the bottom. And then the last one is phi, which is, what was phi again? Oh, it's the phi is the angle with the z-axis. So you have spherical coordinates, you have two angles and one line, okay? That determines the location. Now please look at, to see the description of these three angles. You can see it very nicely depicted here. See, theta is the angle on the bottom, on the xy plane, whereas phi, that Greek letter there, phi is the angle that's made between the rho, that is the line that connects the point to the origin, that makes with the z-axis. So that's the three definitions. And with those two angles and one line is enough to determine the location in space. Now the conversion relationships are on the next page. And there are two sets of conversion relationships, converting to the rectangular coordinates that we're familiar with, and even converting to the cylindrical coordinates that we just studied. Now to know the details, the conversion is longer. For example, x equal to rho sine phi cosine theta. Now, and then if you look down here, there is a graph and a short description about 6 lines. See, here are 6 lines that describes why the conversion works. That's the sine and cosine, and let's see, is my thing focusing? Anyway, please stare at this graph and read these 6 lines right here, okay, as part of your homework. And that will, because the explanation is actually just basic trigonometry, okay? That's and plus the Pythagoras theorem, of course. So between you figure out the side and sine and vertical and the base, and which is sine theta and which one's the cosine theta and all that stuff, and then you see that the entire definition makes sense. So please do that as part of your homework. And with that, let's go to the next page, page 237, where there's a quick description of what happens when each of the coordinate is a constant. Now, if rho, which is the distance, the only distance in the spherical coordinates, if rho equals to a constant, that makes that is just a sphere, okay? Because well, as you can imagine, if the radius is constant, it spins a circle, which in 3D is a square. I mean, it's a sphere. Now, if theta is constant, it's similar to the cylindrical coordinates, where you shoot out a half plane along the direction of theta. And lastly, if what is this? If phi equals to c, now the book has a slight error. It says phi equal to 0 here. They mean phi equal to c, okay? The others are all equal to c. See, rho equal to c, theta equal to c, phi is also equal to c. And so that's just a slight typo. Now, if phi equals to c, then you get a half cone. The reason we call it a half cone is because normally a cone has both ends, you know, a top cone and then a bottom cone. And so it's like the half plane. This is a half cone when phi equals to some constant. Now, that just gives you a basic idea of how cylindrical coordinates work. And so with that, please do example 2.63, which is converting from spherical coordinates back into rectangular, I think. And next, example 2.64, going from rectangular into spherical and cylindrical coordinates. And then next is flip. Okay, and that's about it. So please do example 2.63 and 64, which are busy work, as part of your homework, because it will give you a good solid grasp of the different coordinates. I forgot to mention example 2.65, where you identify surfaces, as we just mentioned, where rho equals to something that's a sphere, etc. So please do example 2.65 as well. And with that, we come to the next example. We'll skip it because that's like no part of that is interesting. So what? You convert latitude and longitude into spherical coordinates. What does that do? That doesn't change anything at all. And then 2.67 is not that big a deal. Choosing the best coordinate system, that really just depends on the situation. There is no strict rule of choosing. Your book wants you to think that if your object is round, then you tend to choose the cylindrical. If it's more like a cylinder, and choose the spherical if it's more like a sphere. But really, nowadays we have the computer. Doesn't matter how you choose it, it works out nicely. So we'll skip that. And with that, we have come to I believe we have come to the end of this section. So for homework, please do section 2.7, page 246. Please do problems 365, 69, 75, 83, 87, 91, 97, 99, 401, 5, 9, 13, 17, and 21. And I will not be talking about any of the problems because they are all busy work, let's just say. There is but there's no way around it because it's the only way you can gain a good understanding of these different coordinates. And of course, doing grunt work always builds character. And imagine how much character you will have when you're done with this homework. So please do that. And that's the end of this section.